Okay, so this will be the second last lecture. So we will start with wrapping up what we started last time, and that is the Lorentz group. And then we will move on to some more general concepts and to the classification of Lie algebras. So last time we had seen that we had the Lorentz group, and it was generated by some boost generators and by some rotation generators. And we could actually form linear combinations of those such that they formed sets n plus and minus, which didn't mix. That is, the commutator between n pluses only gave something in the n plus set, and the commutators of the n minuses only gave something in the n minus sets. And then we could split these up into different representations according to which transformation they transformed under for n plus and then minus. And we studied the 1/2 zero representation and the 0 1/2 representation. We also introduced the van der Waals notation with dotted and undotted indices. Today we will finish this up by considering the so-called 1/2 1/2 representation. So now we have both a dotted and an undotted index. Interestingly, this will be possible to translate to the ordinary 4-vector transformation. After that, we will move on to the Poincare group. So aside from ordinary Lorentz transformations, boost and rotations, we will now also include translations. Then we will talk a bit about more general concepts. So we will sort of pave the way for the classification of Lie algebras by introducing the killing form / the Cartan metric. So it's essentially a sort of scalar product in the algebra. Before starting, I also like to say that hand-ins will be available on Friday at 1 p.m. on the website, and then they should be handed in next Friday at 5 p.m. I also like to point out a little typo that I found. In absolute size, it is as small as it possibly can be, because it was there was a missing dot here, but that dot is potentially that the absence of that dot is potentially confusing. So epsilon here does not change the dottedness structure of this object. So this beta is contracted, and there is a remaining free index alpha dot, and so there must be a dot over that index. And since this is all new, it's potentially confusing, and so I'm pointing it out. A student also alerted me to the fact that there was some mismatch in contraction of Lorentz indices at some point with some metric, but I think that was not confusing because this is stuff you know already. Okay, so then we move on to the 1/2 1/2 representation, or so-called 1/2 1/2 representation. So for this representation, we will have one index of n plus type and one index of n minus type. So we will have 2 copies of SU2. So we will have some objects roughly of this form. However, as is conventionally made, actually we will not take exactly this object. Instead, we will remark upon the fact that we will have here 2 times 2 equals 4 indices, and that is also the number of indices we have for a matrix. So instead, instead of actually using, quickly speaking, a direct product representation, we will use a matrix to represent a similar object. So we will then use a 2 times 2 matrix, and the general 2 times 2 matrix M can be split into a Hermitian part and an anti-Hermitian part. We will soon see that the Hermitian and the anti-Hermitian parts, they do not mix under Lorentz transformations, and therefore, if we had them both, we would have a reducible representation. So we will consider only one of them, and we will consider a Hermitian part. There is also another reason for that I will come to. So what we do then is that we consider a general Hermitian matrix, and we form it by taking a form momentum p mu and contracting it with sigma mu, where sigma 1, 2, 3 are ordinary sigma matrices, and sigma 0 is this guy, diagonal 1, 1. So after the contraction of the mu index here, we will have some 2 by 2 matrix p alpha dot beta. So my tongue slipped here, and I called this a form momentum. So indeed, it can be a form momentum, but in fact, it can be any four vector. As we will see, there is a reason for calling it P as in form momentum, but we can think of it as a general four vector. The logic will be exactly the same. Okay, so we take this general four vector and we contract it with sigma mu to form this object P alpha dot beta. So it is P0, gamma and sigma 0, P1, sigma 1, P2, sigma 2, P3, sigma 3. And now we want to write this as a matrix. To see what we have, we see that this P0 part multiplies 1, 1, so the P0s, they end up here. And we see that the P1 part is multiplying off diagonal 1, 1, so they end up here. Similarly, the P2 parts end up here with a minus sign from there and the plus sign from there, and the P3 parts end up on the diagonal like this. Here, since we are now dealing with relativity, we have to be picky about index positions. So note here that we have lower indices, and when we rise them, we do rise them as we do in relativity. So P upper index 3 is minus P lower index 3, and these are the upper index guys are the ones that correspond to actually the physical momentum in Z direction. Okay, so we write it then in this way, where we have just introduced the minus sign for all the spatial components in order to be able to write it in terms of an upper index guy, because this is what corresponds to the actual momentum if you want, or position if you want. Okay, so now we want to have a look at how this object transforms. This is the main task here. So to do so, we call the transformation of the indices in question. So we have here one upper dotted index that was the left, and then we have here also an upper undotted index that we achieved by complex conjugation from this upper dotted index. So let's transform this P alpha dot beta as we normally transform tenses. So that is, we have one transformation matrix for each index. So acting on the first index gamma dot, we have lambda alpha dot gamma dot, and on the second index delta, we have lambda beta delta. Okay, so I write my first matrix, it goes here, and my second matrix, it goes over there. So what is done in the first part of the expression here is just that I insert the form of lambda alpha dot gamma dot. So this, since this has a lower gamma dot, it should then act on something with an upper index, upper dotted index. And that was just what we refer to as the left chiral representation. So I take this guy, and I remember the form of it. It was a minus sign for the rotations and a plus for the boosts. Actually, if you look at this, I do nothing to this expression. It just follows through all the way down here. So nothing happens to it. This is my P comes from there. And then I take this representation. So recall that the dotted and undotted indices were related by complex conjugation. So actually I should just have the complex conjugate of what I have here. So I have plus I, and I have a sigma star there, and a sigma star there. I have components beta, delta from there. There they are. Okay, so to this object I will do something. So it would be very neat if it was daggers instead of stars there, because the sigma matrices are Hermitian, so then I could ignore the dagger. So what I do is that I replace this sigma star with the transposed object. That is, I dagger it, and to compensate for that, taking the other set of indices from before, I also swap the index order here. So here it's beta delta, and here it's delta beta, with position being important. So I take so essentially I transpose it, not essentially, exactly, I transpose it, and I take the component delta beta instead of beta delta. So I do nothing, of course. But the purpose for doing so is that then this sigma star becomes a sigma dagger, and the sigma dagger is sigma. So in the next step, what has happened is that the daggers have been removed here. And what's also nice is that now this looks like a transformation of a matrix. So here it was the direct product definition, and the standard tensor transformation. So one transformation rule for each index. And now, also by this transposition take, I have cast it into a form where it looks like a matrix multiplication. So it's 3 index alpha, same as on this side. And then it's gamma dot contracted here. And then it's delta contracted here, and 3 index beta. So now this looks like a matrix multiplication. And this is the point where we pause to note that this thing is summation, because if we sorry, that, okay, so this thing in the should say is that if this object is Hermitian, it is mapped into a Hermitian matrix, because this guy and this guy cancel, such that it's if you take the conjugate, Hermitian conjugate, we still have something that is Hermitian. One can see that by Taylor expanding the exponent here and here. Okay, so this guy is Hermitian, so as promised, it doesn't move into the anti-Hermitian component. So we consider we start with something Hermitian, and we have a Hermitian matrix after the transformation. So now that was the general form of the transformation. Now we will have a look at a boost in Z direction. Z is nice because sigma 3 is diagonal. So what I do then is that I take my general transformation from up here, and I note that I only take the component multiplying sigma 3, so only sigma 3 is there. However, not for the rotation part, but for the boost part. So I then just have one boost parameter, say eta 3, but I call it eta here. So this guy goes here. And similarly, I just insert a boost with only something in the sigma 3 direction. So I have this guy here, and actually I have now the same sign here and here. Okay, so what's happening in the next step is that this is just written out. So recall here that my sigma free is diagonal 1 minus 1. So exponentiating this diagonal matrix is trivial, it's just exponentiating the matrix elements. So I have then for my first element e2 simply eta over 2 here, and for my second element coming from here I have e2 minus eta over 2. Here I have my p, momentum written out, and here I have again the same matrix as over here, because it's plus sign in both places. This is easy. So what happens is, for example, that this element here, if we multiply a plus eta half from here and a plus eta half from there, so it will be e to plus eta times what it was. This element from here, it will pick up a plus eta from here, but it will pick up a minus eta from here. So those terms will cancel, and it will be exactly what it was before. Similarly, this element down here will pick up one plus and minus and be mapped to itself. And this element here will pick up a minus from here and a minus from there. So we will have e to minus eta, what it was before. Okay. So to conclude, we have that the p prime, which is then the primed coordinates. So p0 prime, p3 prime, and here minus p1 prime plus I p2 prime, etc. That is then equal to this object here. So this object here stands here, copy pasted. Okay, and the nice thing about this is that now we can start identifying components. So, for example, if I look at this component here, it goes here, and it is then equal to this thing here. So I have e2 eta p0 minus p3 standing here. And similarly, I have this component here. There it stands, should be equal to this component here. There it stands. For the off-diagonal entries, I note that nothing has happened to them. So this fits with p1 prime being p1 and p2 prime being p2, and the same here. So they are not transformed. Okay, so now I expand out my e to eta. So this is just cos h eta minus sine h eta, and here, sorry, from here. This is from here. Cos h eta minus sine h eta, and minus sine from there. And from this guy with the plus sign, I have cos h eta plus sine h eta. And the nice thing about this now is that if we look at it, we see that we can solve for the transformed version of p0 and p3. So we can solve for p0 prime and p3 prime. So, for example, if we add those two expressions together and divide by a factor of 2, we should identify p0 prime. So adding them together, I have a cos h from there times p0 and another cos h from there times p0. Then I divide out the 2, so it gives me this term. And I have a minus sine h from there multiplying p3, and that comes with the same sign as a minus sine h multiplying p3 down there. The other terms cancel. So I have minus sine h eta p3. So this was how my p0 changed. And similarly for p 3 prime, I just to solve for p3 prime, I just take this guy minus this guy such that those cancel, and by the same basic linear algebra steps, and then left with the minus sign h eta p0 and the cos h eta p3. And now I hope that this rings a bell for some of you, because now we can actually take what we have learned here, so those in combination with the fact that nothing happened to the p1 and p2, and we can compile it into one matrix. So we take then a p0 prime, a p1 prime, a p2 prime, and a p3 prime, and we write here the coordinates for p0. So p0 prime was cos eta p0 minus sine eta p3. So this multiplication gives us the new p0, and p3 prime was minus sine eta p0, 0 p1, 0 p2, and cos eta p3. So I get these transformed vectors slash I get this transformation matrix, and I hope it looks familiar to you, because this is nothing but the ordinary Lorentz transformation that you should have seen in special relativity, and I guess general relativity as well, and possibly even more basic physics courses, but then probably without the eta. So eta here is the rapidity. So the cool thing is that we have recovered the vector representation, so the ordinary 4-vector representation of the Lorentz group, by using the direct product representation. So from the 1/2 representation, we can get the ordinary 4-vector transformation. So actually, we could have implemented our transformation rules in relativity by working with 2 times 2 Hermitian matrices, and then multiply them with matrices from both sides. But of course, that would be pretty inconvenient. So not at all natural, coming from the sort of background one has when going to relativity. So what one does is always this thing. See it as a matrix acting on a vector. It's of course simpler, less steps in the multiplication. Okay, and now I want to make a remark upon P here and my saying of calling it momentum. So indeed, actually, this is why I call it P. We often have, indeed, of course, momentum is a 4-vector, and so it can be seen in this form, just as can be transformed this way as other 4 vectors. But actually, what is probably not known to many of you at all is that we can also use this form in the Dirac equation. So I'm not assuming that you know the Dirac equation, but I know that many of you do. So the Dirac equation is the equation that we use to describe a free fermion field. And it has this form with some gamma matrix, which is some off-diagonal sigma bar. This I gamma I mu, this is essentially the momentum operator. So I have something along the line of p dot sigma, p dot sigma. Now I can write it in this form with this p here. So I can write it as p mu some sigma mu, and then actually I would need to have exactly the p that I have used here with upper and upper dotted and an upper undotted index. And down here I would need something with a lower undotted and a lower dotted index, such that it can act on this Dirac spinner, which I then write as a left chiral part with an upper dotted index and a right chiral part with a lower undotted index. So this is just an aside, but for those doing particle physics, it's quite nice to see that it fits with the the Dirac equation and the structure of it, and that we can actually it's even quite natural to treat momentum in this way, to view the momentum as a matrix. And actually, it is a completely straightforward exercise to prove then that if the 4 vector is massless, that corresponds to the determinant of this a matrix being 0. One can also construct higher representations of the Lorentz groups in similar ways. So here we had the 1/2 representation, and we obtained it from the direct product of the 1/2 0 representation and the 0 1/2 representation. Recall that the Dirac spinor here was the direct sum representation. Here we have the direct product representation. We're not going to at all go into depth, but it turns out that in general one can form direct product representations of also higher left and right chiral representations when in the reduced, that is reduced into a direct sum representation, the j's individually go from the maximal j to the minimal j obtained by standard SU2 addition. So recall, of course, that these and plus and the minus, they corresponded to SU2, so that's maybe not a complete surprise. Okay, I skip the rest. I consider it slightly beyond the scope here. And then instead I move on to the Poincare group. But maybe before moving on, I should ask if we have questions. You are welcome to interrupt with questions at any point. Okay, so I receive no questions, so then I go on. So what is the Poincare group? Well, it is the Lorentz group combined with translations. So x goes to x plus something, or t goes to t plus something. And since the Lorentz group was split into 4 components according to the determinant being plus minus 1 and gamma 0 0 being plus minus 1, so we can similarly decompose the Poincare group into 4 so-called different components that do not mix under ordinary continuous transformations, but one would need to again involve the time and space reversal operators to mix between them. And as for the Lorentz group, we will study the component with the plus plus components, so determinant 1 and gamma 0 0 logarithm 0. Okay, so the new structure here is the translation. So let's for a while assume that we have just one dimension. We will have sort of 4 copies of this in the end. So we have some function of x, and now we want to translate it to x plus epsilon. Now this is then the original function times ddx of the function multiplying epsilon. So this is then an infinitesimal translation, or essentially the first term in a Taylor expansion. Now, since we are physicists and we like to insert the little i's and use Hermitian operators, we do that as well in this case. So we define our p to be I dvi, and we then we can then expand our function phi of x as phi of x going to phi of x plus a as e to I some ai contracted with pi if we allow for general direction here, and then acting on the phi of x, and then we can write this as some translation vector I guess it should be mu here if we're considering general directions. Yep. And I think it would be nicer to allow for mu direction there as well. Okay, so we have an equation of that form for each direction. And now again, we want to represent this as a matrix. So we consider them, actually write it in this form. So we have a 4x4 block, which is our ordinary Lorentz transformation. Now this is of course in the 4-vector representation. And then we have some lying vector here, 4 long. Here we have 4 zeros, and here we have a 1. And now let's see what happens if we take this matrix. Here it stands and acts on this object here. So of course, from the first element we have lambda xt, there it stands, and then this one will be hit by this a vector transpose. So this one just goes here. The lower component will be this vector multiplying that this guy, so it will be just the 1 hitting the 1 there, so it will remain a 1. So actually, since we have here a bunch of zeros, so this 0 is 0, 0, 0, and then it's a 1 there, but since all of those are 0, nothing will happen to the 1 here. It will not be affected by what's standing up here. So the 1 will remain a 1, so it's a little trick in this transformation. Okay, so in this notation then, the infinitesimal generators of translation are given on this form here. So they should serve the purpose of generating their translation as we had upstairs, and they should not touch this piece here. So that's the additional generators of translation, and then on top of that we have the old generator. So on top of that we have generators of form big case there, 4x4 blocks, and then zeros in the other columns and rows. And similarly, of course, we can have, instead of case, we can have else here. So the old Lorentz generators. And then in terms of those matrices, the generators of the Poincare groups is the generators of the Lorentz group plus the generators of the translation, so plus these guys. Then in terms of that, one can write down the algebra. So the algebra is then obtained by straightforward matrix multiplications. And we see that first we have what we had before, the rotation generators, I and j essential gives the third remaining rotation generators. We take rotation generator I with the boost generator j, then what remains is the last index boost generator k here. And if we take the commutator of 2 boosts, we get something proportional to the last remaining rotation generator. So that was the old Lorentz algebra with the else, so the rotations in principle forming a subgroup, but the boosts certainly not forming a subgroup, because commutator of two k's give us an L. Now to this Lorentz algebra, we add this set of commutator. So if we take the commutator between rotation in I direction and a translation in the direction, it's I epsilon I dk and translation in k direction. Rotations and time translations commute. This is probably quite intuitive. Boosts and translations in space give us something for only if the index is the same, and boosts with boost involving coordinate I combined with a time translation gives us a translation generator corresponding to the same index. So actually this now looks quite complicated. I think it is quite complicated, but there is a way of condensing these equations and writing them in a neater form. So the strategy for managing with that is to, instead of labeling the rotations by the axis around which things is rotated, label them by the plane in which the rotation happens. So this is also, of course, a much more generalizable concept. If you rotate around the axis, you need exactly 3 dimensions, such that when you define the plane, there is only one remaining axis. So possibly it should not be super surprising that if we instead label generators by the plane that is involved, and that plane could then be both, say, the xy plane for rotation, so any other spatial directions, or the tx plane for boost in x direction, etc. So now we take the same set of generators, but we just rename them slightly. So we take our Li and define it as epsilon I jk m jk, where these are then the directions in question being involved, and this is of course just plus minus 1. And ki a boost in I direction, that is mixing 0 and I direction, so this is then m0I. Then if we cast the algebra into this form, we can collect these commutators in a somewhat more compact form. So first, nothing happened to our generators of rotation, sorry, of translation, and they still stand here. But the commutator of rotations in boost hiding in m with translations in row direction can be cast into this somewhat shorter form. And similarly, if we take rotations and boosts with himself, there is a one-liner for all of these statements up here. So it's a slightly more compact form. Any questions to that? And then I come to something interesting. Then we can ask ourselves, what Casimir operators can we have for this group? Well, it should be things that are left invariant under all group actions. And you already know that the momentum square is such a thing. So momentum square, as you are well aware of, this is momentum squared. It's the invariant mass square. So this is of course unchanged for boost, quotations, and translations. So this is one of the Casimir operators. But actually, what is far less known is that there is another Casimir operator. So there is something called the Pauli-Lubansky 4-vector, W mu. And if you contract it with itself, that is another 4-vector. And this Pauli-Lubansky 4-vector, it is obtained by the fully antisymmetric combination of generators M on one side, so for two of the indices, and a translation generator, so essentially momentum for the other direction. So actually, this is something like the Lorentz invariant version of spin. But there is such a quantity that is fully Lorentz invariant, and that is the Pauli-Lubansky 4-vector squared. Actually, I think I must change this. It's not the vector itself; it's the vector squared. I should also point out that this group is, so the Poincare group is not a compact group, and the representation that we have here is not unitary, because as before, the case do not correspond to something unitaries, and also the P generators does not give us anything unitary. So we have then a non-unitary representation of the group, and in fact, since this is a non-compact group, so the boost generators can take on any value going to the boost parameter eta can take on any value going to infinity. So the group is not compact, and that also means that there is no finite dimensional unitary irreducible representation. Yeah, okay. Also, to connect to all the quantum mechanics knowledge, I think it's probably clear, but I pointed out anyway that this P mu corresponds to the energy momentum operator. In this M mu is then related to angular momentum. And the fact that we have two Casimir operators here, so we have P mu contracted with P mu, giving us some M square, and the Pauli-Lubansky vector square. This means that we have two different set of values to characterize the representations of the Poincare group. So the mass is one of them. So mass is a Lorentz invariant, or mass squared is Lorentz invariant. It's the same statement. So that is used to characterize transformations of the Poincare group, and also spin is used to characterize the representations. And aside from having a mass, then the particles that we encounter are spin 0 objects or spin 0, 0, so 0 for the n plus and 0 for the n minus objects. And the only fundamental Lorentz scalar that we know is the Higgs particle. There are others as well, but they are not fundamental like the ions. Then we have spin 1/2 representation, as we have said, that is the 1/2 0 plus 0 1/2 representation. So that is applicable to fermions, so that is applicable to electrons. And we have their cousins and quarks, and then we have spin 1 representation. And those that have taken the particle physics course know that we have some object A and U for the photon. this spin 1 representation or 1/2 representation is then used for protons. It's also used for the strong cousins, the gluons, and for the W plus minus and Z coming from the weak force. And this brings me exactly to where I wanted to end. So let's see if there are any questions. If there are no questions, then I'll sit here in front of the computer for a few minutes and see if someone wants to ask. And I suggest that most of you take a break, and then we meet again at 1/4 past. So since I don't hear any questions, I take that as there are none. So this is just to say that I'm by the computer if someone wants to ask about the lecture or perhaps about the exercises. So, hello and welcome back. It's time to continue the lecture. So I just want to conclude a bit with what we did last time, so the last half of the lecture. So I think there are a few main points. One being that we covered the ordinary Lorentz four-vector transformation from a direct product representation. And the other one being that we studied the Poincare group, which was essentially the Lorentz group plus translation. And in this case, we had two Casimir operators, one being the very well-known mass grid and the other one being the far less famous Pauli-Lubansky four-vector grid. And actually, this Pauli-Lubansky four-vector is some contraction of epsilon, and we will connect to this in one of the exercises because we will study the Lorentz transformation of epsilon, and we will actually see that this is another invariant, and in fact this invariant of the Lorentz group is related to the determinant being invariant, which is also far less known than the metric / scalar product being invariant. Okay. So if there are no questions to that, maybe actually later you have questions about the exercises. I'm not 100% sure for some of them how manageable they are. So I'm happy to help you. So maybe you want to ask questions about that after the lecture. But now let's move on. So we will define some more general concepts and we will make steps towards classifying the algebras. So here things will become a bit abstract. So I will define the concepts of a simple group, a semi-simple group, and a simple algebra and a semi-simple algebra. And those concepts are used then later on for classifying the algebras. Okay, but here we go. So simple Lie group. A Lie group is called simple if it is not abelian and does not possess a continuous or Lie type invariant subgroup.
Malin, you have not shared your screen.
Thanks. Of course, I should fix that. Good. Okay, now you should be able to see it. Okay, so we will talk about simple Lie groups and semi-simple Lie groups and simple Lie algebras and semi-simple Lie algebras. So a Lie group is called simple if it is not abelian and it does not possess a continuous, so Lie type invariant subgroup. I should perhaps remind you as well that a subgroup H of the group G is invariant if and only if for all the H's in H, the action of G brings you back to an element in H. So let's think about a few examples. So this is actually a pretty counterintuitive definition because first of all, UN is not simple because it has an abelian subgroup. The diagonal face, that would be an abelian subgroup that you can have in UN. You cannot have it in SUN, and SUN is in fact simple. Furthermore, of course, then not even U1 is simple because it's abelian in itself, and the simple groups are not allowed to be abelian. But SU2, SO3, and also SUN are simple. Then we come to the concept of a semi-simple group. So a Lie group is called semi-simple if it is not abelian and it does not possess a continuous abelian invariant subgroup. So it can contain invariant subgroups of this type, but those subgroups are not allowed to be abelian. So at least semi-simple is perhaps slightly more simple than slightly less simple than simple. So why are they called semi-simple and simple? So in what sense are they simple and semi-simple? So we will see that the semi-simple groups we can split up into simple groups. So they are some sort of sum of simple groups, and therefore they are semi-simple. Okay, now we will define the analogous concepts, but at the level of the algebra. So at the level of the algebra, if one can linearly combine m infinitesimal generators, so m smaller than the smaller than the number of generators. So we take m out of n generators, and then if the commutator of those generators stay within the set, then those commutators that will then generate the invariant subgroup, they form a sub-algebra. And if in addition it is the case that if we take a commutator with one of the other generators and we still stay among the elements in the subalgebra, then we have an invariant subalgebra, also known as an ideal, and the Lie group will possess an invariant subgroup. And that this is the case can be seen essentially by exponentiating this. So we take e to Baker-Campbell-Hausdorff, and if we have g's and a's mixed, and we have some, if the commutator is always some a, then when we exponentiate, we'll just get series of a's. So simple. So the concept of invariant subalgebra is clearly very relevant for the invariant groups. Okay, so now to the concept of simple Lie algebra. So a Lie algebra is called simple if it cannot be split, or more precisely, if it is not abelian and it does not possess an ideal, so it cannot be split into another ideal, apart from the null ideal or itself. So essentially it's simple if it cannot be split. Semi-simple Lie algebra is not abelian and it does not possess an abelian ideal. So it can be that the algebra can be split into invariant subalgebras that satisfy this as well as this, but it's not allowed to possess an abelian ideal. So not all commutators here are allowed to vanish. And this is then semi-simple in the sense that it can be split into simple Lie algebras. So simple groups in simple words can be split into semi-simple groups can be split into simple groups, and in this way they are halfway simple, so semi-simple. And semi-simple Lie algebras can be split into simple Lie algebras, so in this way they are halfway simple, so semi-simple. Okay, here we have the statement that every simple Lie algebra is a direct sum simple Lie algebras. So there exists a set of invariant subalgebras such that the algebra can be split into different such subalgebras, and I've already touched upon it. And this is a useful quality for classifying the algebras and hence the group. Now, this actually also means that every semi-simple Lie group is the direct product of simple Lie groups. So if something is a direct product, if a group is a direct product of a few other groups, and we know how to treat all those other groups, we know how to treat D essentially, and therefore it is at least semi-simple. So a matrix group is simple, semi-simple, if and only if its Lie algebra is simple or semi-simple. So as an example, consider the SO3 algebra. We had it given in terms of commutators like this. Here, there is no smaller set of generators Li that is closed, so we cannot find. So we can find one simultaneously commuting generator, but it only commutes with itself. It doesn't commute with the others. So there's no invariant algebra, and the algebra is not cannot be further split. So the algebra is simple, and so the group is simple. SO3, of course, has the same algebra as SU2. So SU2 is simple, then SO3 is also simple. Okay, so now let's maybe first see if there were questions to that. Then move on to some concepts. So I will talk about the adjoint representation. Adjoint, many of you will recognize from particle physics as adjoint representation for gluons, for example, or weak bosons. And the adjoint representation is a very special representation because it's one that can be obtained directly from the algebra relation itself, as we will soon see. So I will talk about the adjoint representation, and I will talk about the killing form, so-called killing form, which is related to the Cartan metric, or which is some sort of metric on the algebra space. And we have essentially encountered a metric before. It's essentially the trace. Okay, so now we go back. So we go back all the way to the Jacobi identity that we had. Here it is. It's all the cyclic permutations A, B, C of this guy here. This was one of the constraints we had on an algebra. If this was not fulfilled, we said we didn't even have an algebra. So this we require from an algebra, and it is trivially obtained, as we have seen, by just straightforward matrix multiplication if we have a matrix representation. However, this Jacobi identity actually gives rise to a particular representation, the adjoint representation. So we have seen that from this, the Jacobi identity, we could obtain this relation here for the structure constants. Maybe I should say that I'm now using, for a while again, the mathematician's convention. So it's E2 generators, not E2I generators. But this here is actually nothing more but a representation of the algebra in disguise. So let's see what we can get from this relation here. So this is just the relation copy pasted, and now we will move indices around a bit. So if I look at the first C, it's exactly the same C below, so nothing has happened to it. Then if I take a look at the second C, it's also exactly the same. So the first term is exactly the same. Then in the second term, CJLM is the same, but I have swapped the order of the I and the K indices for the second C, and this is compensated for by minus sign. Similarly, in the second term, the last C is the same, but in the first C, there is an order swap again of K and L. And now I make the definition that adjoint representation of EI, it remains to see that it is actually a representation. We will find that it is. Component JK is CI Annoyingly component kj, but it's just a sign, so don't worry so much. Okay, so we have this, and we replace c's up here with this relation here. So the first c is then adjoint ei, because the first index stands. And then it's component ml, because up here it was lm, and they should then cross down there. And similarly, other c's are translated. So then it's adjoint ej, so j stands, and then k and l swap place. Then it's minus c ej, and lm and m swap place. And then it's c ei, and k and l swap place. And then it's minus el from cl, and k and m swap place. And the last c is just standing, nothing is happening to it. The nice thing about this so far random seeming transformation is that now we have passed it into something that looks again like a matrix multiplication. So if we look here, we have a dummy index L here in the middle, we have a dummy index L here in the middle. Last term, there is no such thing. So the three indices here, that is M and K. So this can be seen as adjoint EI from there, adjoint EJ from there, and then component MK from M and from K for the first term. And if you look at the second term, it's the same story. So dummy summation L, we can view it as component MK of a matrix multiplication between adjoint EJ and adjoint EI. For the last term, we have a component MK already of adjoint EL, and the CIJL just stands. So this is still 0. So then what I do is that I take this term and I just move it to the other side. So it gives me this term down here. And I note that here I have the commutator between EI and EJ. So EI, EJ, EJ, EI. So this is just this commutator of which I take a component MK. And this term moved to the other side, I also take component MK, but now this should be true for all M and Ks. So it should be true at the level of a matrix equation, and not only for some specific component MKs. So I have then the adjoint EI, adjoint EI, adjoint EJ commutator is then CIJL adjoint EL. And now, hopefully this looks a little bit familiar, because commutator of element I and J equals to CIJL element L is exactly the defining relation that we had for the algebra. So the important finding here is that the structure constants, the CIKL, do themselves form a representation, because this adjoint here was essentially just C. So the structure constants can be used to form a representation. They always give rise to a representation, the adjoint representation. And now, if there are n linearly independent generators, then this algebra sorry, yeah, then this adjoint representation is an n times n representation. So for example, for SU3, we had actually 8 generators. So the adjoint representation must be an 8 times 8 dimensional representation, which we pretty much never write out as 8 times 8 matrices because that's pretty clumsy. But if we use it, we essentially use it in this form, but we are physicists, so we rather use something like FABC. So those that have seen QCD may remember that this is a factor that's encountered for the strong force in vertices with gluons. Okay, so actually we could have written the commutator relation as the adjoint representation EI component LKEL. And we can similarly represent a general element A in this way. And for the commutator, the following properties hold. So the commutator is linear. So we have we can break out an alpha. If we have alpha A, and we can break out also a constant for the second argument, so it's clearly linear. And also the adjoint representation of the commutator is the commutator of the adjoint representation. So it forms an algebra. So recall, it's not just the commutator relation must be satisfied in order for it to be an algebra of the group in question, but it must also be linear and the commutator must remain in the algebra. So questions to this?
Yes, one question. The sum from L to N, and then you have an for down a bit. Then you have I equals to 1 to N. Is that just a mislabeling?
Yes, it very much looked like it. Yes. So the sum here is over the repeated index L, and there isn't even an I in there. So this seems like a typo. It seems to me that this relation should actually go up here. What about that? Well, it fits, but you can then say the same thing for K. So yeah. Yes, that seems to be a typo. That's sort of details that I don't see. So thanks for pointing it out. Any other comments or questions? Okay. So before moving on to defining the killing form, I like to stress what I've said before, that the adjoint representation is important in particle physics because the gluons live in the adjoint representation, so there are 8 gluons and t squared minus 1, and also for the weak force, the SU2 left part of the weak force, we have 3WI, so that's 2 squared minus 1 equals 3. Then we will define the killing form, and I think of this as a metric. So the killing form of two elements A and B in the algebra is defined as the trace of their product. Clearly, this is a symmetric operation, so the trace is cyclic, so you can move the A to the other side. So it's obviously symmetric. It's clearly also linear in A and B, so it's bilinear. So it fulfills a lot of the properties that we expect from metrics. So it's, I mean, what's the point of defining a scalar product and the metric? Well, I think the point is that you should be able to use your intuition for scalar products and metric, because that you have some sort of intuition for. And scalar products are defined because the mathematical concepts are encountered in many different situations in physics, for example. And I think it's the same for groups. Why do you define the concept of a group? Well, it's because objects with exactly those properties are encountered a lot of times. So it makes sense to define the abstract concept and talk about general properties of that concept, the group, so that one can generalize it to many different situations and many different groups. So here we have a metric, and yeah, go on and think about it as a metric and use your scalar product and the linear space intuition. Okay, so we take down, so if we talk about the killing form of some elements EI and EJ of the Lie algebra, it is defined in the same way. So D, EI, and here it really starts to look like a metric D mu nu in relativity. So that is D of EI, EJ is then the trace of the adjoint representation of EI and the adjoint representation of EJ. So we can write it out in components as well. So viewing this as a matrix multiplication, we have a dummy summation index k for the middle index, and then for the trace, well, this is taking component L of this big thing, and therefore we have an L there and an L there. And by the way, in this form, the cyclic property of the trace is entirely obvious. If you have forgotten it, you can see it from here. And then recall that this adjoint of EI was some CI and then LK, but with components swapped. So instead of LK, we have KL. And similarly here, we have CJ, and instead of KL, we have LK. So we have this thing here. So this, in terms of structure constants, is then the killing form. So it's defined for the adjoint representation. And then indeed, this metric like a quantity is also known as a metric. It's known as the Cartan metric. We have to think about it as a scalar product in the physicist sense, where we allow for negative norms. So just as in space-time, if we take something purely in the x direction and square it, we have something negative here. We must also, in general, allow for negative quantities. Then, if we consider the case of an SUN algebra, so a very important special case, then the C's were antisymmetric in all the indices. And if we use this form here for the IJ, it's the same thing. And observe that we can swap the order at the expense of a minus sign. So we have the I is standing here, the J is standing here. Here we had KL But if we can swap the order of those and gain a minus sign, so that minus sign there, then we have component KL square. So then we have this guy square. So the structure constant square IL with a minus sign. And note here that this thing here, it's something square, and it's a real number square, so it's clearly positive. So this thing is negative. So in fact, in the mathematicians' convention, without an I in the commutator and without an additional I in the exponent, this GI day is negative. It's even negative definite. But if we had inserted and used Hermitian generators instead, so if we had used the physicist convention, we would have essentially mapped the generators to I times the generators and compensate with some I in the exponent as well. And clearly that I squared compensates for the minus sign there. And in this, and this we need if we want to connect it to what we have spoken about as a scalar product in the context of SU3 and SUN. So for SU3 it was the Gell-Mann matrices, and then we multiplied them together and took a trace, and then we saw we got delta Ij. So it was on the contrary positive definite, but that was because we used the Hermitian generators, so the physicist generators. The point of defining this, aside possibly from using scalar product intuition, is that we need it for classifying Lie algebras, because it turns out that many of the structural properties of the Lie algebras can be read up from the killing metric. So there is a famous theorem from Cartan saying that a Lie algebra is semi-simple if and only if its killing form is non-degenerate. So the determinant of this guy is not allowed to vanish. Also, and so the proof of this is beyond the scope of the course, and similarly, we also have the statement that for real Lie algebras, the algebra is compact if the Cartan metric is negative definite, so negative definite for the mathematician. And this was the case for positive definite for the physicist. So for the physicist convention, we saw that for SU3 we had the trace lambda A, lambda B, essentially being delta lambda A B. And I am not going to, so actually the factors of 2 that you see here and there, the normalizations, they are all conventions, so don't worry so much about them. But yeah, we had a factor 2 there. And one can, so the killing form in the adjoint representation is that one has to take traces of pretty big matrices, for example, n squared minus 1 for SUN, but it can be related, and one can cast the algebras into comparable forms such that one has the same killing form in other lower dimensional representations. So, for example, we can study the SU2 Lie algebra in the mathematician convention with anti-Hermitian matrices. And then one way of representing them, so first way we saw them actually, I think, was this way. So it's anti-Hermitian minus 1, 1. So always a minus sign in one of the places. And if we multiply them together and take the trace, we quite easily see that we get 0 if we take two different ones of them, and if we take the one guy with the same, so for example this one will hit this column and it will produce a -1 standing there, etc. So by fairly quickly one can convince oneself that the killing form for this adjoint representation is some minus sign in the method conventions. It's a factor 2, and then it's the identity matrix. So essentially it's the identity matrix. Do we have any questions to that? If not, we will move on towards the classification of Lie algebras. So I should say immediately that what will be presented is not a full classification, but I will rather give a taste of why it so happens that one can only have a limited number of Lie algebras, because we will see that there are quite strong constraints on the possible sort of weight planes, where one can have, similarly as we did for SU2, we had all the JZ values, and for SU3 we had a two-dimensional plane. But the fact that we should always, for all the lowering and raising operators, we should always end up on other points in the representation, that gives us constraints, giving that we cannot have all possible relations between those points. They are in a sense quantized. Okay. So we will here study a general Lie group. We will have n generators, and we will have some m generators in a Cartan subalgebra. Then we will have non-Cartan generators, which cannot be cast in a diagonal form at the same time. So the rank of the group will be m, because there are m generators that can be diagonalized at the same time. So just to remind you, ignoring normalizations, we could have that for SU2, our Cartan element could be J3, and the other ones could be J1 and J2. For SU3, they're simultaneously commuting generators for T3 and T8, and the others, so non-Cartan generators, would then correspond to the other 6 generators. And we could not find more generators that commuted at the same time. So if I took the spin Z axis, I could not take the spin X or the spin Y axis at the same time. That didn't work. Now, in general, to study the weight diagram, so the corresponding thing to all possible sets, we want to form linear combinations of the non-Cartan generators, such that those linear combinations are step operators. So this is what we did for SU3. So we had the T's and the U's and the V's, plus and minus. They were all step operators. Okay, so if we start with, so actually, before starting, I should also say that it's not obvious that we will manage with this task, because we want them to be step operators with respect to all the different HIs, and possibly one can think of the algebra as being some sort of intertwined multiple SU2s, and for each of them one should be able to find step operators, much like this, but it's not at all clear that one will find step operators that are step operators with respect to all the different HIs. But we did actually manage in the case of SU3, because we saw that the T's, the p plus minus, v plus minus, and the v plus minus, they were simultaneous step operators for both the T3 and the T8 at the same time, so that worked. Okay, so what we do then is that we start with one HI, so one element in a Cartan subalgebra, and we form linear combinations. We want to form linear combinations, and I denote them E alpha I, but it's I denotes that it's related to this HI. Linear combinations is just a sum over different EAs of the original non-Cartan generators. And what I want is that the commutator of HI with that guy, commutator with of HI with that guy should be that guy. That is what I want. As well, up to a constant lambda. So this relation here is then to be compared to L3, so the Cartan element commuted with L plus and L minus should be, in that case it was L plus and minus, and here we have some constant that we allow for. Then we make use of our killing form. So we take the expression that we have up here, and we multiply it with EB, and we take the trace. So that is, we take the killing form, and I denote it in this way. So here we then have the killing form of this element with this element. This piece here comes from this piece here. So I have here used that the commutator between HI and EA was, in the physicist convention, IAC EC. So this is just inserted here. So the structure that remains is the EC. So it is only the EC that must stand together with the trace, or in the killing form with EB. The other constants I can clearly pull out. Then this here was then GCB, because this was the Cartan metric. So what I have here is some constant I times something real and antisymmetric should then be equal to my lambda from up here, my VA also from up here should be an A, and then the Cartan, the killing form of EA and EB down there. So since we assume that FABC is real, so this guy here is purely imaginary, and it's also antisymmetric, and therefore it is Hermitian and has real eigenvalues, seen as a matrix operation. So now have a look at this expression here. So we call this CAB. So we have some VA CAB. So it's like we're multiplying the vector from the left with this matrix. And this is some vector multiplication from the left with this matrix. The summation over A we can let be implicit if we want. So what we have here is this thing. And we are searching for eigenvalues fulfilling this, so it corresponds to this determinant being 0. And it's time to stop here, but next time we will use this together with the so-called fundamental theorem of Cartan, which says that there is only one. It says that the eigenvalues are non-degenerate, so there is only one eigenvector for a certain eigenvalue, and this will allow us to simultaneously diagonalize the effect of all the HIs on the special linear combinations alpha here. But that we will have to finish up next time. So it's time to stop, but let's first see if there are questions. So if some of the groups that are going to present on Friday would want to ask me some questions, you're very welcome to do so as well. Or if anyone else wants to ask. But with that, I think we say thanks for today and see you for the last lecture on Thursday. So I say bye for those of you who do not want to ask additional questions. So let's see if there are any questions to the material or the exercises or anything else.
Hello?
Yeah.
Yeah, I had a question. I wrote it in the chat as well.
So I cannot really multitask enough to read the chat and give a lecture at the same time.
Yeah.
Will any form of no, they will not. It's actually quite interesting. Whenever there's a written exam, no one asks for the question in advance. But whenever there is an oral exam, people want long lists or short lists, perhaps, of questions. I am not at all persuaded that providing such lists is helpful. So I know that it's frequently done in introductory courses where students are new to university and possibly have a hard time finding out or understanding what is the most relevant material. I think that when one has been a student for some 4-ish years, one has learned that. So it's not as needed, and actually I doubt that it actually fulfills any meaning. So I have no intention of giving such a list.
Okay.
Any other question? Okay, so then I think we finish for today. So I say bye. Bye.